So the first thing will be metal plus non-metal, metal plus normal water, sodium with normal water, potassium with normal water. Again, I'm going to show that to you. We're going to see how the sodium reacts if we put sodium into the water. Okay? Are you ready?
Yes.
All right. So this is sodium, and the sodium is kept into the liquid. And do you know what kind of liquid is that?
Oil.
Mineral oil, isn't it?
Yes, it's mineral oil. Why do I put sodium into the mineral oil?
Because you can't put it in water.
Yeah, it cannot really react with the oil, but it may react with other chemicals or other liquid. So, do you want me to have a big size or a small size?
Big.
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 Okay. Big.
We like fire.
We like that. Now I will put this sodium. Can you see this sodium? This is sodium. And I will put this sodium into this normal temperature water. Okay, this is not hot water again, this is normal water. That is another observation. And I'll add a few drops of phenolphthalein.
Yeah. It'll be all pink. Oh, it's gonna be so cool. I'm
This
so
is DI water,
excited.
no color change. Now let me put it aside. If somebody die, I'm not responsible for it. Kind of responsible. Maybe for it. We'll see. So I'm having some protection here. I'll drop it there into the DI water, then I'll run. You don't run, you stay here. I'm just kidding. Depending on the situation, you'll run. Are you ready?
Yeah.
Okay. Sodium into the normal temperature water.
Oh, it's turning pink.
Oh. Oh my god! Oh my god.
Wow.
Are you all okay? Oh my god.
All right, what do you think about that, Owen?
It wasn't big enough. I think we didn't go big.
I think we could have had a bigger explosion.
Worst ever. Some coughing, there is some sort of gases. Also, the observation can be we're all scared. Okay, so now are you ready for potassium? Oh, did I put the phenolphthalein into the DI water?
No, not yet.
Not yet. Why do I put phenolphthalein into the DI water?
You can see the change in pH.
Okay. All right. Now pray to the God. And ready? 1, 2.
Yay.
Okay. Definitely there is a gas. The color changed. Fire. It didn't burst.
Yay. Look at all these good note takers.
Any other observation you see here?
Very pink.
More pink now?
It's very pink.
Okay. And we feel like, as there was an explosion with the sodium, so we might have a tendency to feel like that sodium is more reactive. But do you think the reactiveness only depends on how much fire was there? Does it really only depend on that one? What are the other factors?
How much gas was produced?
Say that again.
Like the hydrogen produced?
How much hydrogen was produced there? So which one was having more hydrogen?
Potassium.
The potassium one, right? And how about the other perspective, like the color? Which one was having more pink color?
Potassium as well.
Potassium. So if very from the superficial perspective, it looks like sodium was more reactive. But if we look into the amount of hydrogen gas, if we look into the amount of fire, and if we look into the color of the normal water, change of color of the normal water, which one was actually more reactive? Potassium. Can you say that? Maybe yes?
Yes.
Okay. So let's say we agree that potassium was more reactive. All right. So that's what we have practically seen, right? Practically we have seen that potassium was more reactive. Now let's go back to the theoretical perspective. Just try to imagine that long time ago, like 200 years ago or 300 years ago, when the scientific equipment was not that very highly advanced, maybe one of the scientists found this element, sodium and potassium, somewhere, and the scientist is doing some experiment and put those two elements into the water. And the scientist found potassium is being more reactive. Now let's say 200 years have been passed, and now we have more technology, more advanced instrument. Now we know how many electrons are there inside this element, how many protons are there inside this element, right? So now with this advanced technology, we know the atomic number of sodium and atomic number of potassium, right? Can you please tell me what is the atomic number of sodium?
Sodium is 11.
11.
Yeah, and then potassium is 19.
Okay. So, how many electrons sodium has?
Oh, 11.
11. How many proton it has? Someone else.
11.
How many proton it has? Equal number of proton it has inside the nucleus. So let me draw the structure of sodium. And this is the regular structure of sodium. With the advanced technology, we know it. Let's draw for potassium. It has total 19 electrons on the orbit, right? And how many protons it has?
19.
Equal number of protons it has inside the nucleus. So the last one will be in the fourth orbit. That is the regular structure of potassium, right? Now, if we want to compare the regular structure for both of the elements, we see both of them have one electron in the outermost orbit. Just one electron, right? But which one is farther away from the nucleus?
Potassium.
Potassium? We all agree on that? So for which one it is easy to lose the electron? For potassium, right? So if some element easily loses the electron, it can react more easily, right? If it loses the electron very easily, that means it reacts very easily with other elements. So theoretically, we can say potassium is more reactive than sodium. Okay, so we convinced ourselves that our practical data and theoretical data for those two reactions were same. But actually what happened? When we analyze it more, we can see potassium was actually more reactive. Okay? Any questions? No? Okay, then we can start working on the other activities and enjoy the last lecture.